Thank you for the introduction. And I will talk about a joint result with Ejine Santul and Erika Fornaroli from Maringa State University. Well, it's been a long time since I gave a talk with the same title in Malaga, but the main result that I gave there was for a poset of length 1. And since then, we managed to generalize this result to an arbitrary poset, an arbitrary finite connected poset. So that's the result that I will be talking about today. Well, this is the outline of my talk. I will give an elementary introduction, yes, starting from the very basic things. And then I will give a description of Lie automorphisms of an incidence algebra. Well, a quasi-order on a set is just a reflexive and transitive binary relation. And a set equipped with a quasi-order is called a quasi-ordered set. Or pre-order. These are two notions that I used in one. Authors prefer to use quasi-order, the other authors prefer to use pre-order. And a partial order is a quasi-order which is anti-symmetric. Which, well, the difference is the following. In a quasi-ordered set, you may have elements x and y, distinct elements x and y, such that x is less than y and y is less than x. In fact, you have some equivalence relation generated by this. And in a partially ordered set, you cannot have two distinct elements with this property. So if x is less than or equal to y, and y is less than or equal to x, and then they coincide. So a partially ordered set is called poset for short. Okay, if you have a quasi-ordered set, you may define an interval or segment between x and y to be the following set, which consists of all z which are between x and y in the sense of your quasi-order. Well, I'm using this a bit unnatural notation for the interval, for the closed interval, because I will be using the usual square brackets for the Lie product. So it's almost square brackets, but just to make them different from the square brackets, yes. So examples, well, a set is called locally finite if all its segments are finite sets. Examples, n natural numbers with the usual partial order is an example for locally finite poset. But if you add the infinity as the maximum or the greatest element, which is greater than every natural number, then it's not locally finite anymore, because you have segments with the right-hand side equal to infinity, which are not finite. Well, any segment except the trivial one is not finite of this form. And for example, the real numbers with the usual partial order is not a locally finite poset. Both of them are posets, but yes, not quasi-ordered sets. Well, if you have a locally finite quasi-ordered set and a commutative associative unital ring, you may consider the set of functions of two variables on your x with values in R. Those functions which are 0, which take value 0 whenever x is not less than or equal to y. For example, if x and y are incomparable, yes. Those functions have usual R-module structure, and if you would define the multiplication using the convolution formula given here, observe that it makes sense exactly because your x is locally finite. So this set of z is finite here, so this sum is finite. And if you define the multiplication this way, it gives you an associative unital algebra over R, And it's almost never commutative except for the case where X is an anti-chain, except where any two distinct elements of X are incomparable. So this is an associative algebra, yes. Well, examples, the full matrix algebra is in a particular case of the incidence algebra. If you take X to be an n-element set, where any two elements are, well, if you take your quasi-order to be equal to X squared, like shortly speaking, for any X and Y, X is less than or equal to Y, okay? And another example, if you take the usual, if you take a chain, if you take, for example, for the set of from 1 to n, with the usual partial order on natural numbers, then you take, well, you obtain the upper triangular matrix algebra. So these are two examples. And more generally, if you take a finite set X, finite poset or quasi-ordered set X, then you might, if you enumerated its elements in the appropriate way, then you can view the elements of your incidence algebra as n by n matrices. So you can then the product of functions becomes the usual matrix product, and you may embed your incidence algebra into the matrix algebra, the full matrix algebra. And moreover, if your X is a poset, if your order is partial, not a quasi-order, then you can embed it into the upper triangular matrix algebra. So these are two like canonical examples or paradigmatic examples. So any algebra, incidence algebra will be a subalgebra, either of this one or of this one. And that's why they are sometimes called structural matrix algebras. There isn't a theorem which says that, which characterize those subalgebras of the matrix algebra which are incidence algebra, but this is not the topic of this talk. There are some technical conditions. Well, another point of view on incidence algebra is the following. You can view its elements as formal series. Of course, this EXY is just a symbol. X, okay, the sums goes through all the elements X and Y of the ordered pairs X and Y, and alpha XY is the constant, the element from your base ring. And you multiply these two sums using the product of these two symbols, to EXY and EUV. You multiply them as if they were matrix units. Yes, if you imagine it, is as matrix units, as a matrix which has 1 on this position, this entry, and 0 otherwise. In fact, if X is finite, so these sums are finite, and it's nothing more than the semigroup algebra of the following semigroup. Yes, you should adjoin 0 to make the product of two elements to be equal to 0 if they are not, if Y is different from U. Okay, we shall use the notation B for this set of basis elements. Observe that we require here that X is strictly less than Y. We just this will be useful because we'll be working with the basis of the commutator ideal, and this is exactly that basis. Yes. Okay. What about Lie maps between associative algebras? Okay, a Lie homomorphism is a map which preserves, which respects Lie product, and the Lie product is, or the Lie bracket is the bracket is the product which which could be associated to any product in fact, but for associative product, this gives you a Lie algebra, and it even gives you a Lie algebra in some more general cases, as we saw in this school. But for me, it will be useful. It will be sufficient to use only this definition only in the associative case. Okay. And okay, if it's bijective, it's called Lie isomorphism, and if it's from one algebra to itself, then it's called Lie automorphism of A. They form a group, and this group will be denoted by L out of A. Well, some examples, some canonical examples are homomorphisms. Usual homomorphisms are Lie homomorphisms. Negatives of anti-homomorphisms. So you take anti-homomorphism, okay, if it exists, and you take its minus, yes, it gives you a Lie homomorphism. And somehow trivial example, if you take a central valued map which annihilates all the commutators, and so this gives you Lie homomorphism because if you look at this property, it gives you 0 equals to 0. Well, and of course you can add the maps of different types. More specifically, if you add a map of type 1 or 2 and this central valued map, then this sum is called, we will call it proper. Well, what about descriptions of Lie isomorphisms or automorphisms for some known rings? Well, an old result of Martindale, if you have a Lie isomorphism between prime unital rings, such that this ring has characteristic different from 2 and 3, and it has a non-trivial idempotent, then any Lie isomorphism is proper. Moreover, this map will be an isomorphism or the negative of an anti-isomorphism. Yes. In particular, you can see that this holds for a Lie automorphism of full matrix algebra over a division ring. Okay, so this result you just require additivity, not linearity. Okay, because there are rings. Well. So for full matrix rings, any Lie isomorphism is proper. What about upper triangular matrix rings? Again, this is a more recent result comparing to the previous one. And if you take R to be an indecomposable commutative unital ring, indecomposable means that it has no non-trivial idempotent, then any Lie automorphism of the upper triangular matrix algebra is proper. It's sum of an automorphism or the negative of an anti-automorphism and some central valued linear map. Okay. Well, some more general case when you take upper block triangular matrix algebra over a unique factorization domain of characteristic different from 2 or 3, then again any Lie automorphism of this ring is proper. So up to now, we had no examples of non-proper Lie automorphisms between several kinds of matrix algebras. Okay. So what about Lie automorphisms of an incidence algebra? We will restrict ourselves to the following more or less easier situation where X is connected and finite poset, and R will be a field. Although some results could be proved without any change, I think in the case of indecomposable commutative ring, and of course finiteness is used. Well, it cannot be omitted in our proofs, of course, because we're using the basis, and which is not a basis in the infinite case. Yes. And what connected means is that for any two elements of your poset, you have a path or a walk between them, which means that you have a sequence of elements which connects these two elements. And the sequence is the following. Each two consecutive elements of this sequence are comparable in your poset, and there is no element between them. Okay, This is just the last condition is just technical one, because in the finite case, yes, in the finite case, you can always extend your path to the path which is in some sense has no intermediate. You could not insert intermediate elements between two consecutive elements. Okay. Well, and we introduce some ideals which will be necessary in our proofs. This is just the commutator ideal. So this is the ideal generated by all the commutators of two elements. And we consecutively define by induction, we define I would call it the M commutator ideals. Yes, so you commute J1 with Jm minus 1. And that's why you define it for all M greater than 1. Well, these ideals could be described in a very easy way. Let us define Lxy to be the length of the interval xy, which is the following. It's the maximum length of chains which start xy in x and end in y. So the length of maximal chain between x and y. Of course, if your set is finite, this always exists. So it's a finite number. For an infinite set, it could be infinite, of course. Well, for a locally finite poset, it cannot be. But for non-locally, it could be. Okay, and in fact, the ideal J is just spanned by all EXY, where X is strictly less than Y. It's just the set B, which we introduced above. That base is B, which we introduced above. And for any M greater than 1, you can describe Jm as the ideal spanned, well, the subspace of which is the ideal, spanned by all the subspace spanned by all this EXY, where XY has length at least M. So you see that in the finite case, okay, your length cannot be arbitrary big, because it's limited by the cardinality of your x minus 1. So at some point, this ideal vanish. But for a locally finite poset, although these numbers are finite, as I said, but they could not, in some situations, they could be unlimited. So they could grow unlimitedly, and that's, in this situation, your J will not vanish. No? So all the ideals will be non trivial. But in our case, at some point, they vanish. Okay, it would be useful for us to decompose the ideals into the direct sum of subspaces. The subspaces are formed by linear combinations of basis elements, which correspond to EXY of length exactly M. Yes, and for convenience, we denote by G0 the whole incidence algebra. So L0 would be spanned by EXX, and would give you what is called the diagonal subalgebra of your incidence algebra, which could be seen as the if you view your incidence algebra as a subalgebra of a matrix algebra, so this could be viewed as the subalgebra of diagonal matrices. Okay, and it's obvious that the ideal Jm has this decomposition into the direct sum of subspaces. Well, now, if you have a Lie automorphism, yes, you take a basis element which belongs to Lm, so xy has length m. You apply your phi to this basis element, and since your phi preserves ideals Jm, because the ideals Jm were defined in terms of the Lie bracket, and phi preserves Lie bracket. So the image of EXY belongs to JM, and you could separate the part which belongs to LM and the rest. And the rest would belong to JM plus 1. And this part, which belongs to LM, the same LM, we denote by phi tilde of XY. Well, you could easily prove that this gives you a linear bijective map, but it's not very easy to prove, but that it gives you in fact a Lie automorphism, and we will see this a little bit later. To this end, we will use some lemmas, which are interesting itself. Well, let us define by Bm those basis elements which correspond to xy of length m. Let us denote by x squared less the set of pairs xy, where x is strictly less than y. And let phi be an arbitrary automorphism of the incidence algebra. So I said this guy here is some linear combination of the EXY with XY of length m. In fact, it's unique element, basis element of this type, multiplied by some constant. So this phi tilde, it induces a bijection of your basis, of the basis of your commutator ideal, and it works in the following way. It maps EXY to this theta xy multiplied by some constant sigma xy. And we will now, we have one more lemma before we proceed. So this was the description of this part here. What about the rest? Is it arbitrary? In fact, it's not arbitrary. It should belong to the ideal generated by this element, basis element, which belongs to Lm. So you have here a basis element from Lm multiplied by some constant plus something which belongs to the ideal associative or Lie ideal. In this situation, it's the same, which generated by this guy. Well, and these are two crucial lemmas which permit us to prove that the map phi tilde is also a Lie automorphism of the same incidence algebra. Okay. Moreover, this map which associates your phi tilde to phi is an endomorphism of the group of Lie automorphisms. So if you take the composition of two Lie automorphisms, it goes to the composition of the corresponding tilde maps. So moreover, if you apply this twice, if you consider tilde of tilde, then it's the same as taking tilde once. So automatically you have some semi-direct product decomposition of your group, and later we'll be talking about this decomposition. But first of all, we will denote the image of this map by L out tilde, and the automorphisms, the Lie automorphisms which belong to this image, we will call them elementary. So elementary Lie automorphisms, they work as follows. They map Lm, well, any element of Lm, to an element of Lm. Of course, since everything is finite dimensional, since phi is bijective, in fact, you have equality here. But okay, a priori, if you would try to define elementary for a Lie homomorphism, then you would require only inclusion. Okay, and moreover, we saw that it acts more specifically, it acts as follows. It takes the basis elements to a multiple of some basis element. Yes, it's inducing some bijection between them. Well, we will describe elementarily automorphisms a little bit later. It's the main part, but we first describe the kernel of this map. Okay, elementarily automorphisms, they form the image. What about the kernel? And the kernel is in fact the group of inner automorphisms of your incidence algebra, but not all of them, those which are conjugations by elements with ones on the diagonal, whose diagonal is the unit of your algebra. So this beta D means the diagonal, and delta means the identity element of your algebra. Again, this is not an easy to prove fact. It's a consequence of some series of lemmas, which are not present here. Okay, some technical lemmas. So you have direct product, semi-direct product decomposition of your group, in which this term has already been described, and we are left to describe this subgroup. And this will be the rest of this talk. Well, so now we will always be talking, we will always be working with elementary Lie automorphisms. Well, okay, being a Lie automorphism, it induces the maps theta, the bijection theta of the basis of the commutator ideal, and it induces that sigma, which corresponds to the coefficients. Yes, these two maps will be fixed, and as a consequence of the proposition of the lemma, in fact, you see that phi acts on the basis of the commutator ideal as follows, multiplying. Okay, I'm just repeating what I said, but in the case of an arbitrary automorphism, you had a rest here, but now it's not appearing, it's 0. So phi acts on the commutator ideal as follows, very easily. We'll discuss some properties of these maps theta and sigma, because they are not arbitrary, of course. Theta satisfies the following. If you take two basis elements whose product is non-zero, yes, this product of two elements exy and eyz is exz. So theta either preserves this product or inverts this product. So theta acts as a homomorphism or anti-homomorphisms depending on the pair of elements. Yeah, and in the case where it acts as a homomorphism, where it preserves the product, the corresponding sigma satisfies one cocycle condition. And whenever it reverts the product, the corresponding sigma satisfies the one cocycle condition with minus here. And I will say that sigma is compatible. Okay, now I'm considering an arbitrary bijection of the basis beta. I'm considering an arbitrary map of two elements sigma. I say that it's compatible with theta if one of these two conditions hold, depending on whether this holds or this holds. Observe that these two conditions cannot hold at the same time. So this guy cannot be equal to this guy. They could be equal only if both of them are 0, but it's not possible because theta is a bijection, so this cannot be 0. So it makes sense, this definition. Okay, and I said that theta preserves product or inverts product for any two elements which could be multiplied, whose product is non-zero. Well, in fact, it could be extended, this property could be extended to maximal chains in X. You take a maximal chain in X, remember that X is finite, so such a chain is always finite. And your theta will map, well, the pairs from this maximal chain to the pairs of some other maximal chain of the same size in the following way. It preserves the order or it inverts the order. Okay, only two possibilities. So theta, it induces a bijection between maximal chains of your poset in a way that a maximal chain goes to another maximal chain, preserving the order or inverting the order. Okay, so I say in the first situation, I say that theta is increasing on a maximal chain in this situation. And in the second situation, I say that theta is decreasing on the maximal chain C. And if theta is either increasing or decreasing on any maximal chain of your X, then I say that theta is monotone on maximal chains in X. So I'm using this notation, this terminology from calculus, maybe. And okay, so not any theta, not any bijection between basis elements could be the theta of some Lie automorphisms. But again, as I said, this condition is okay. This condition is necessary, but we'll see that it's not yet sufficient. To get a sufficient condition, we will consider some natural valued maps associated to a bijection of your basis and some closed walk in X. Closed walk is a sequence of elements of X such that any two consecutive elements are comparable and there is no element between them in your poset X. So one of them covers, which is called, we say it covers the element when there is no element between them. And okay, walk means that you could repeat elements here. So you could, okay, you cannot repeat. Your next element cannot be equal to the previous one, but it could be equal to some of the previous ones, some of them. I know, for example, the third one, okay, the third one could not be equal. The fourth one could be equal to the first one. Okay. And I associate to a bijection and to gamma 4 functions. Okay, let's see in details how these functions work. This function, 2 S functions and 2 T functions. S functions, S comes from the word source and T comes from the word target. Okay, S functions, S function, S plus, it works as follows. We count all the pairs UI plus 1 in this walk, which appear as theta of some either ZY, ZW, where Z is this argument here. In other words, we have our Z. We consider all the edges which start at Z. We apply theta to all these edges and we count those of them which appear here in our closed walk. Moreover, they appear in the same order, preserving which in the same order. So this means that UI is less than UI plus 1. And if the order is reversed, then the number of such pairs, such W's, in fact, gives you S minus. And we have two similar functions for those edges which end at Z. Yes, those which we count the images in gamma in the same order, or those which appear in reversed order. So those four functions. Since our set X is finite, these functions take, okay, and since walk is finite, of course, these functions take natural values. Observe that I consider natural numbers with 0. So some of these functions could be 0, of course. A lot of them could be 0. And if your phi is an elementary automorphism, you take theta corresponding to this phi, you take an arbitrary gamma, then the functions, the S functions and T functions, they satisfy the following condition. The difference of S functions coincides with the difference of T functions. And there is an example, yes, and I call theta admissible if it satisfies this condition for any closed walk gamma in X. In particular, if your X has no closed walks, this means that X is a tree. So the Hasse diagram of your poset is a tree, then any bijection theta would be admissible. But of course, there are posets which are not trees. And the example is the following. We take X to be a 2-crone, the following poset. So 1 is less than 3 and 4, 2 is less than 3 and 4, 1 and 2 are incomparable, 3 and 4 are incomparable. Let us take gamma to be 1, 3, 2, 4, 1. And let us take theta to be the bijection which swaps, which permutes 1, 3 and 1, 4, and does not change 2, 3 and 2, 4. Yes. Well, let us see. Let us take Z equal to 3. So in this, let's verify this equality for Z equal to 3. Okay, you take, there is no age starting at 3. There is nothing above 3. But there are two edges which end at 3. And these are 1, 3 and 2, 3. What about the images under theta? The image of 1, 3, yes, is 1, 4. And it appears in this walk in the reversed order. The image of 2, 3 is 2, 3. And again, it appears in the reversed order in this walk. So as I said, since there is nothing above 3, these functions, the source functions, are 0. And the target functions, one of them is 0, that one which corresponds to the pairs which appear in the same order in your walk, and this is T plus. And the other one is 2, because all the two edges, they appear in the reversed order. So you have 0, you have that 0 is not equal to 2, and this theta is not admissible. However, if you take, for example, Z equal to 1, you can calculate that these two functions are 1 and these two functions are 0, and this condition will hold for such Z. So the condition is not invariant under the choice of the Z, and of course it depends on gamma as well. Okay. So this is an example of a non-admissible theta. In fact, we described the subgroup of admissible theta for the sets of this form, which are crones, and this is done in another article, which is a preprint, in fact, submitted to arXiv. But I will not be talking about this this topic today. Well, and so this was these were the conditions of your theta. Yes, it should be monotone and should be admissible to have a chance to be bijection induced by a Lie automorphism. Now, and theta, remember that theta corresponds to the action of your phi on the basis of the commutator ideal. But what about the action of your phi on the diagonal subalgebra, on the diagonal elements? Well, you may show that if two Lie automorphisms have the same theta, yes, I'm not talking about sigmas, yeah, just about theta. And then their actions on the diagonal are fully determined by the action of, by some unique element on the diagonal, in fact. So the action of phi on EZ is determined by the value of this element on one fixed element U0. So everything is determined by one element, and this will be used after in the definition of the triple. Well, now again, this some interesting remark maybe that these sums, they do not depend, this sum does not depend on the choice of u, yes. So the sum of values of phi EZ over all z, it does not depend on u. In fact, it's because it's the image of 5 delta. That's why it does not depend, because this guy belongs to the center, and the center consists of the scalar matrices or scalar elements. Okay, and again, this will be used, and even in fact, the fact that it's different from 0 will be used. Now, the crucial lemma here is that every time you have an admissible bijection, which is monotone on maximal chains, and if you take arbitrary sigma compatible with this theta, then you are able to construct a Lie automorphism, an elementary Lie automorphism, which induces this pair, theta and sigma. So as I said, this condition is now sufficient for existence of a Lie automorphism given this theta. And in the proof of this lemma, you had some kind of liberty in the choice of your phi on the diagonal subalgebra. And this is given in this definition, in fact. Now, let us enumerate the elements of our x as x1, etc., xn. Let us take an arbitrary admissible bijection monotone on maximal chains. Let us take an arbitrary sigma compatible with this theta. And now another ingredient, yes, is a sequence of n elements of your ring. N elements, okay, the number of elements is the same as the number of the elements of X. And those whose sum is different from 0. So any n elements of your field whose sum is different from 0. For example, okay, it always exists. For example, you can take any -1 elements equal to 0 and the final element equal to 1. Okay, given this triple, yes, you may construct an elementary automorphism in the following way. Okay, on the commutator ideal, okay, J, okay, I'm using here another notation, but this is the commutator ideal, J1. On J1, it's defined by theta and sigma by this equality. And on the diagonal, it's defined using the lemmas which we gave before. In fact, as I said, the definition on the diagonal, it's uniquely determined by the values on some fixed element. And I put the value on x1 be equal to cy. This exy means the matrix unit corresponding to xy, xi on the diagonal. Yes. So it's fully determined by this n-tuple of elements of your field. I'm not giving here the precise formula, it's not interesting, but it involves this element and a sum of alternating sum of the sum of differences of your, no, in fact, alternating sum depending on whether your theta respects the order or inverts the order, and it also depends, and it also involves, not depends, involves some walk in your x, and for it to be well defined, we use this admissibility condition. Okay, but I'm not giving the formula, it's not interesting. Okay, and now the main theorem is the following: if you have a connected poset and a field, a finite connected poset, then any elementary automorphism can be represented as tau of this triple, some triple theta sigma s, sigma c, satisfying these conditions here. And in a unique way, one could ask whether could I decompose this guy into some composition of some more elementary maps. In fact, I don't think how, because sigma depends on theta. Yes, so the action of, okay, the action on the commutator ideal does not involve C. Or maybe on the commutator ideal, it could be decomposed in some composition, yes. And the action on the diagonal subalgebra, it involves C and theta, does not depend on sigma. So to decompose it on the whole algebra, I don't see how it's maybe not possible. But in some situation, it's possible. For example, if you have a finite chain, then your incidence algebra is nothing more than the upper triangular matrix algebra. And in this case, you can decompose it in the composition of a automorphism of a, or it should be, yes, or the negative of an anti-automorphism, and some map which acts as follows. It adds some scalar element to EY. And yeah, this situation you could decompose it. In fact, this is equivalent to say that your phi is proper, as I defined above. So we obtain this corollary as a consequence of the main result. Well, and what about non-proper? Do they exist? Yes, of course they exist. And the minimal example is a set of 4 elements. For 3 elements, all of them would be proper. And for 4 elements, just consider the following poset and take phi defined this way. It corresponds to theta. Okay, remember that theta should map a maximal chain to a maximal chain. Okay, for a maximal chain 1, 4, you have 2 maximal chains, 1, 4 and 1, 2, 3. For the maximal chain 1, 4, there is no possibility. You should map 1, 4 to 1, 4. So this is written here. And for the maximal chain 1, 2, 3, there are 2 possibilities. You map it to the same chain 1, 2, 3, preserving the order, or you map it to the same chain 1, 2, 3, inverting the order. And this is the situation where it inverts the order. So see that E1, 2 goes to E2, 3, and E2, 3 goes to E1, 2, and E1, 3 goes to E1, 3. There is no other possibility. Again, this with minus sign here. So this phi is an elementary automorphism, which corresponds to the triple. Okay, theta, as I said, I have already said how theta acts, yes. A sigma is 1 almost for all pairs, but for one pair it's -1 for this one here. And the corresponding C, the sequence of your field elements, is those guys are 0 and the only one of them is 1. Of course, this phi is not proper because essentially because it acts as well, in fact, you may see on the action of this phi on this diagonal idempotence of this primitive idempotence. If it had been an isomorphism or an anti-isomorphism plus some central map, the images of this idempotence would be either EI or EI or EI plus some scalar element, yes. But look, this guy here is not of this form. It's not EI, neither EI plus some central element. So that's why it's not proper. But of course, you can construct a lot of other examples for example, adding one more element here. Yes, you could construct phi such that it preserves the order on this 3 chain and it inverts the order on this 3 chain, as in this example. And of course, only for this reason it could not be proper. Yes, because if it had been proper, it would either preserve the order on any chain or invert the order on any chain, but it could not preserve the order on one chain and invert on another chain. So for X of 5 elements, you could even construct example in a more easy way. So this guy is not proper. In fact, we have an article which describes some situation which gives some sufficient conditions on X for such that any automorphism of the incidence algebra is proper. We described some classes of sets of length 1 with this property. We calculated the groups of Lie automorphisms, the subgroups of proper Lie automorphisms for some classes of these sets, and this is the contents of other article which was submitted to archive, but I will not talk about that. Okay, this is the article whose result I am presenting here. And thank you very much.
Thank you very much. Are there any questions?
Let me see.
I can't see any, but can you see any? There's someone. Okay.
Participants, yes.
Okay. Thank you for your talk. So when I see the hash diagram,
yes.
So the name of the algebra incidence of incidence algebra, has it a relation with the angle of incidence in geometry, or simply NM?
The relation with what? I couldn't understand. Well, if yes.
I said that why we call the algebra incidence algebra.
Incidence algebra. It's a good question. Let me think about that. Maybe because maybe because of the condition on the functions, which somehow which is related on those pairs which belong to your order. So somehow codifies those pairs which form your order. This, I don't know. In fact, it's a good question to to search in the literature.
Okay. Okay.
Maybe it has something to do with geometry, as you said. I don't know.
I comment here. The matrix, there is notion of incidence matrices for graphs.
Yes, of a
So
graph.
it's
Yes.
0, 1 if the
Yeah. Maybe
connect.
this. I see.
It is
If
a
you realize
generalization
your
of this.
yes. If you realize your incidence algebra as okay, if you consider the Hasse diagram of your incidence algebra, yes, it's a graph. So you may take the incidence the incidence matrix of this graph, which consists of 0 and 1s, and 1 is exactly at the position which corresponds to x less than or equal to y. Maybe by this reason, yes. But as I said, the elements of your incidence algebra could take values different from 1 as well. But yeah, maybe by this reason, but it makes sense.
Okay. Thank you. Any more questions or comments?
I have a quick question, please.
Mhm.
Yeah.
Are there relation to Alexandrov topologies on finite sets? You have these Hayes diagrams.
Mhm.
They remind me to, you know, when you consider topologies on finite sets, is there any relation somehow?
Topology, well.
Because topologies on finite set, these A0 topologies, they call them Alexandrov topologies. It's the same thing as these pre-orders. You can describe them basically by Hayes diagrams.
I don't think that they are the same as pre-orders, but you can define some topology of your set
using the
using an
posets.
order. In
I mean,
fact, you
this is
can define
well known.
you can define, yes, but I'm not sure if any topology could be realized as a topology of some finite poset.
No. I'm saying I'm considering only topologies on finite set, precisely the Alexandrov topologies. Depending of your this is the A0 topologies. Anyway, just when I saw the Hayes diagram, that made me think of this, but it's just general question.
Yeah.
I mean, I don't have any idea.
I see. I understand. I understand your question. If there is a class of topologies which could be uniquely determined by some finite poset, maybe.
Right.
Yeah, but I don't know.
Okay.
It's a good question.
Well, thank you.
Any more questions or comments?